I have the privilege of moderating a wonderful program by my good friend Jerry Richmond, who, as you can see, was also a teacher scholar in 1986. Jerry has been an incredibly proficient and creative physical chemist. She's done wonderful work that pushed the boundaries back in this regard. But she really has transformed the way that the state of Oregon interacts with its universities, and for the better. She's going to be talking today about molecular processes at the water's edge, and I hope she'll include at least a few comments about the program she started at Oregon and has gone national and international, called COACH, a way to teach young women faculty how to expect to get the same sort of advantages in terms of environment for their research programs as are available for the men. So Jerry, if you'd come give your lecture.
Good morning. So it's my job to make sure you stay awake for at least an hour, is that right, or 45 minutes? Thank you, Marianne. First, and most important, I want to express my gratitude to the Camille and Henry Dreyfus Foundation, because when I won the Teacher Scholar Award, it was just at such a critical point in my career. I had just moved from a small college to the University of Oregon, and it was one of the first awards that I won. And you know, those first ones are the sweetest, and in many respects the most important, because they give you some validity in the institution that you're at, but also nationally. So please accept my sincere gratitude for having done that back in 1986, and to all those that have followed. Today what I'm going to talk to you about is something having to do with water. And as you know, water is one of the most plentiful compounds on the planet. And a lot of the chemistry that we do and we know about happens in water, but there's also a lot of chemistry that happens on water surfaces, whether it be on the surface of lakes or rivers, or as important, on the surface of water particulates in the atmosphere. And in fact, we know in the atmosphere that a lot of the chemistry that we used to think about was important in the atmosphere as gas phase reactions, a lot of that actually happens on the surface of ice particles and liquids, aerosols above the oceans. And so trying to understand the chemistry that happens on a water surface is very important. And we know so little about that. We know a lot about how gases interact with solid surfaces, semiconductors and metals, but we just haven't had the tools in the past to be able, even up until today, we haven't had many tools in order to explore just very simple processes at a water surface, which include how water, how any kind of a gaseous molecule, when it absorbs or bounces off of a surface, what's the interaction as it reaches the surface? Or if some gas molecules don't bounce off the surface, but they actually bounce and stick a little bit, and then can go on up or down. And did I miss my little guy that jumps in? Oops, I can't back up. Well, here we go, bounce off. There's my guy that dives. So there's some gas molecules that then jump in and dive in, and they don't even notice that the surface is there. But we don't know which ones are which. We don't know which ones are going to stick, which ones are going to go in, which are going to bounce off and go back and forth. And so that's exactly the kind of science that we've been involved in with a particular project, and that particular project has been to study sulfur dioxide at a water surface as a first model compound. So to be able to understand, what we'd like to be able to do is characterize gaseous absorption at a water surface at the level that we have for solid surfaces, and that's be able to understand the diffusion of the gas molecule to the water surface, and then what happens when it gets there. Does it adsorb? Does it desorb? Does it dive right into the water and get solvated? What are the processes involved in that gas actually going in or reacting with that surface? And when you think about it, particularly with aerosols in the atmosphere, the surface area is so large on those aerosols that these surface reactions can just be a really critical factor. And up until this point, what most people have done in studying aerosols and uptake of gases is exactly that. They've measured how much stuff goes in, but they don't understand the role that the surface has played. The only time it's speculated that the surface has played some kind of a role is when the uptake doesn't fit with what the thermodynamics would suggest. And so that's what we've been trying to do, is to be able to probe what happens just at the surface, and in this case for sulfur dioxide. Now, sulfur dioxide, of course, is a very important gaseous molecule. It comes from a lot of different sources. It comes from our volcanoes in the Northwest, and it also comes, of course, from coal, where any sulfur-containing coal, where then as the coal is burned, the sulfur is changed to sulfur dioxide. Sulfur dioxide goes up into the clouds, it gets oxidized by ozone and other compounds, and then concentrates in clouds, and then you get the acid rain that results from the sulfur dioxide. So we're going to talk about what role does the water surface play in SO2 uptake. And I'm going to give you a multiple choice exam at the end, and these are your three options. So if you want to be able to come up with the answer, you have to listen to the next few minutes. And we're going to ask what role SO2 plays. Does the water surface play? Does the water surface act as a barrier and not let the SO2 come into it? Or does it act as a doorman that just lets the SO2 come in, dissolve, and then react? Or does it act, or does it act, boy, my clicker, or does it act as the temptress who invites the SO2 in and brings it into its environment? Which of these three? Okay. So SO2 at the vapor-water interface, it's been speculated before by uptake studies and some infrared studies that SO2 actually might form a surface complex before it goes into the solution and then forms ions in solution. And so our question has been, can we see some evidence of it being at the surface? So the questions that we're going to seek with regards to this adsorption process is, what role does the water play in the adsorption and dissolution? And then get a molecular details about what steps are involved and the geometry of these SO2 molecules as they get close to the surface. And then what effect does temperature play? Because, of course, the temperature in the atmosphere is very different than it is here on ground level. And so we'd like to be able to then follow also the trajectory as the SO2 gets closer and closer to that water surface. And so we do this in a couple of ways. We do it experimentally by measuring the vibrational spectrum of water molecules as the SO2 approaches the surface. SO2 is harder to get at, so what we look at with the spectroscopy is the effect of SO2 absorption on the water surface. And so we use a technique called vibrational sum-frequency spectroscopy. The bottom line is we're measuring the vibrational spectroscopy of molecules that are on the first layer of the surface and maybe a couple of layers down, but no deeper than that. And by using this particular technique, which uses a tunable infrared laser and a pulsed visible laser, we're able to measure this vibrational spectrum. And this is just simply showing that we're using a closed cell and also be able to cool it down. And by putting in a tunable and infrared beam on the surface, when the infrared beam is resonant with the vibrational mode of the water molecules at the surface, then you'll get an enhancement in a signal that comes off at the sum of the two frequencies. This process can only happen exactly at the surface where you have broken symmetry, so that's what gives it its surface selectivity. And that allows us then to measure some kind of a spectrum. I'll talk about, in particular for this talk, about the water spectrum when the SO2 is there or not there. And so it's simply just looking at the OH modes of water. We can't get all the information from the experiments, and so what we do is to complement these experiments with calculations. And we have a series of different calculations that we've done for this particular model system. And again, I want to emphasize that this is the first time that anyone has actually done measurements to this level of gaseous adsorption at a water surface. And so what we're learning is not only what the experiments can tell us, but what we also need theoretical work to help us with. And so we do a number of different kinds of calculations. We do equilibrium MD simulations where we basically put a slug of SO2 over the water surface, have them equilibrate, and look at what the behavior of the SO2 is and the water. And then we do other MD simulations where we actually take a single SO2 molecule, we put a little bit of a force on it, and we steer it towards the surface to see what happens to the water and the SO2. and the other are DFT calculations where we calculate bond distances and geometries and figure out what the details are about SO2 as it gets to the surface. Does water come around it? Does water leave it alone? What happens? Okay, so let me just start out with the experimental studies and what the experimental studies tell us. What we have up here is the vibrational spectrum of water, air-water interface. And this has been measured by us very early and Ron Shen, but a number of other people more recently. And what this is just the vibrational modes of water at the surface. And what you see is a broad blob and a very sharp peak. So let me just give you a quick view of what the spectrum means as it relates to what I'm going to talk about. If this is the water surface and these are selected water molecules, this very sharp peak here corresponds to water molecules that have one of their bonds up into the air and one of the bonds into the liquid. So your glass of water, there's some water molecules there that kind of have one hanging out here and the other OH going into the solution. And it has the highest energy frequency because it's not hydrogen bonded to many other water molecules. In fact, this guy isn't at all, so it acts like an independent oscillator. So then as you go further down into the spectrum, what you find is the broader feature right there, and that corresponds to water molecules within the first 10 angstroms that tend to be more highly coordinated. So they can be doubly bonded and they can be triply bonded, but they tend to be a few angstroms below this free OH, which is there. And these guys are also much more sensitive to ions which are in solution than this top guy, this free OH guy. And so what this spectrum allows us to do is to look at what happens when SO2 absorbs at the surface, what happens at the very top layer, and then what happens a little bit deeper in the interfacial region. Okay, let's look at what happens now as you blow SO2 over this water surface and see how that spectrum changes. What you find is when you have the SO2 flowing is you get a distinct change in the spectrum in both of the two regions. You get this, and this is at room temperature, you get the free OH, which broadens, and then you get a slight change in the more coordinated water. And so what that tells us is that the SO2 complex actually forms because this SO2 is bonding to these top water molecules and causing a bonding interaction that then shifts that free OH. But then you also have signal down here which indicates that you actually have SO2 going in and forming ions, because when this peak changes, it's usually a result of ions which are forming in those first few layers of water. So it looks as if SO2 bonds to the surface and then it also goes into the solution and it forms ions. Okay, well, is this absorption reversible? What happens when you turn off the SO2? Because this is with the SO2 flowing. When you turn off the SO2, what you find is that this free OH goes back to the way it was, but you have this increased signal as you have ions produced in solution. So once that SO2 is off, that complex goes away. And so, but the ions still stay there because they, in general, because they aren't popping back out again. So what happens now as you go to lower and lower temperatures? We're interested in this to see if possibly it freezes the complex on the surface or how it might alter the rest of the spectrum. And what we find is this is now going to colder and colder temperatures, that actually this free OH broadens, so stronger and stronger bonding, and there's other changes in this region, but let me first focus on this region right here as that SO2 gets closer to the surface. So if you look at this more closely, and we do a series of isotopic dilution experiments in order to deconvolute this free OH bond, and what we find is if we fit the spectrum, what we find is as you go colder and colder, what you find is there's less and less of this free OH and more of a bound OH to the SO2, and increases until you get to the point of about 0, where you get almost exclusive bonding. All these guys that are hanging out there are almost exclusively bonded to SO2. The surface becomes largely covered, and the red peak, which was the truly free OH, basically disappears. So, but when you turn the SO2 off, all of it goes back to normal. So it's only when the SO2 is flowing that you get this complex being formed. But how does the lower temperature alter the uptake of the SO2 into solution? And so we did the spectrum of that, and I just showed you that before, but the point is that there's an increase in that those lower frequency modes. And so what we find is that, yes, the spectra shows that ion formation is increased at lower temperatures. You get a broader, stronger peak at that lower frequencies. And that's consistent with the fact that the SO2 solubility goes up as you decrease in temperature. So again, it's fitting the picture of the thermodynamics, but giving you more information about the molecular nature of the adsorption. Okay, so, but that makes us then think about whether there's a connection between the gas forming a complex at the surface. Is that required in order for it to go into solution, or are they decoupled? Is there some way that we can test that? So for example, does SO2 come onto the surface and then is always, after it forms the complex, does it always go into solution? Or is there a case at which it comes off and you see no hydrolysis or no solvation? So the way that we tested this was to take sulfuric acid solutions and study sulfuric acid solutions. And what we know from sulfuric acid solutions from thermodynamic measurements is that SO2 is inhibited, the uptake is inhibited if you have concentrated sulfuric acid. And back from your freshman chemistry, you can understand that simply because if it goes in, the equilibrium would drive it back to not wanting to form ions. And so when we did those experiments on sulfuric acid solution, these are the results that we got. So this is now the sulfuric acid solution, and this is now the some frequency spectrum of sulfuric acid. It's a little bit different than the air-water interface, but the free OH is largely unperturbed. And I just have two of these spectra at the same temperature because I'm going to do a comparison, so they're just identical. And so what we find out is when we flow SO2 over the surface of sulfuric acid, indeed the complex does form, but then when we take the SO2 off of the surface, it reverts back to the way it was. The surface is exactly the same, as well as the whole interfacial region. So this would show you that the surface complex can form, but it can then not form the ions, so they can be independent of one another. Okay, so now we understand that SO2 goes to the surface, it bonds to the surface, but what do I mean by bonding? Is it really just this guy hanging out there and one SO2 kind of grabs at one SO2, or what type of complex formation is actually happening? So in these simulations then, so we turn now to the simulations to learn more about the SO2 and also what happens with the water. And again, we're going to be doing both the equilibrium as well as the steered MD simulations. And we're looking at, in some cases, we're looking at what I'm going to call neat water, which is just basically one SO2 over it, or saturated, where you're putting a whole bunch of SO2 over the surface. So this is a simulation now, and you can, it provides an intimate picture of what's going on at the surface. This actually helps you with the multiple choice answer too. But what you see is this is SO2. It's kind of making its way down to the water surface. It's kind of taking its time, and it gets down there. But now look at what happens with the water, if it ever comes down. There it goes. See, the water actually comes up to get it. See? Isn't that cool? I think that's cool. But more importantly, notice that this sulfur is largely pointing down in these simulations. Do another one where we're doing the steered simulations, and this guy's even a little bit lazier. In fact, I've had to cut the film. You'll see a jerkiness, and that's just simply because I wanted to shorten it a bit. There we go. But now as it's being, with a very weak force, pulled towards the surface, you see it also goes with its sulfur down. But it's going to go a little bit deeper in the solution. We haven't been able to do a simulation of what happens when it forms ions, but you see as it gets to the surface, it's still sulfur down. And now I did a little jump, little cut, and you can see even as it goes into the first second layer, the sulfur stays down. Also, it gets pulled into solution. So then we did an analysis of the, doing the simulations of the geometry and what it looks like when it gets closer to the surface. And in this case, what we did was we looked at the angle, two different angles, one of which is to look at the two angles, one is which theta and phi. One angle, the theta, measures whether water goes like this or points down like this. And I have to do this over here. And the other angle is the twist. So the first angle is whether it goes like a cheerleader. Okay, so what we found is that, and I'm just going to go through a summary of what we've seen here. What we get are these eye charts that really challenge you to be able to figure out what these are, but I only put them up there just for anyone that might be used to looking at eye charts like this. This is for the neat water surface, this is the saturated water, and these are just the different angles. This is the point at which, this is the dividing line for the surface. This is vapor, this is water. Again, vapor, water, vapor, water. And so, and the two different angles. But what you're looking for are, if you have a homogeneous color up and down, that means everything is completely random in orientation. When you start seeing spots, that indicates to you that there's a preference in a kind of orientation. And when you get a lot of this blue stuff up here for the water, that means that you don't have good enough signal to be able to draw anything out. It's just sort of, that's pretty much the noise. But overall, what you find is at the neat water surface, or water where there's very little SO2 at the surface, that the water tends to be in the plane of the surface. It tends to be oriented like this in the plane of the surface and a little bit down. But then as more SO2 comes towards the surface, it tends to reorient in this direction. The twist, on the other hand, tends to stay be in this direction also, and it becomes much more random then once it gets to the water. The twist seems to move more random as you put more and more SO2 on there. So it's consistent with the movies that we saw before. And that's and the SO2 in these pictures, what it shows is that the SO2 comes down, and again, very similar to the simulation that I showed you, but this provides a lot more details with regards to the exact angles. The SO2 comes down, and even when it goes into the water surface, it tends to stay strongly oriented into water. So what does the complex look like? Again, is it just this guy and the SO2 coming down? So we did a series of calculations on this, and we're naming, there's all kinds of options, and I'm going to name them as if it's bonded to an oxygen and through the oxygen of the sulfur, or through the sulfur, I'm going to call it an SO complex, an O complex if the SO2 is only bonded through oxygen, and here OO through the oxygens. And so when we take the simulations and then we do a counting to figure out how many times these different kinds of complexes show up. It allows us to then do a histogram of the most popular kind of compounds that could be complexed. And what we find is that this particular configuration where water is bonded to the sulfur and then also through its oxygen is the most prevalent, but a cyclic form is most prevalent. And that's through the sulfur. But you see the ones with the big signals are all through the sulfur. Again, that's consistent with the sulfur coming down, both at 23 degrees and at 0 degrees. And these are just showing pictures of what these different kind of bonding configurations seem to be. So it's not just hanging on to one OH coming up, but actually the water molecules do come up and have an interaction. And you can see the ones that are the weakest are two bonded sulfurs or something where you have just the oxygens bond. So again, the sulfur is coming down to the surface. Okay, so to finish up then, and this is my multiple choice question now, what role does a water surface play in gaseous uptake? Well, we know, for example, that as SO2 gets close to the surface, it comes down with the sulfur down. The water molecules then start to rearrange and reorient, and so they come up and actually meet with the SO2. The complex that it forms, this is the most common with the cyclic complex with the sulfur. And so, doorman, barrier, temptress, what's your vote? Temptress? Temptress? Sure enough, sure enough, sure enough. And Mark, where's Mark sitting? Cardillo. So Mark, just so you don't accuse me of being sexist in showing this temptress here, I actually looked on the web to see if I could find a male temptress, and they all came out as being devils. Right? Temptor is the male form of temptress. And so I actually felt that given my age, the more attractive kind of temptor would look something like this. Mark, are you feeling warm and fuzzy now? All right. So let me give thanks where who really deserve the thanks, and that is that. And then I'm going to say a few words, as Marianne requested, about some of the things that we do with Coach. But Teresa Tarbuck started the SO2 work, and then Stephanie Oda has continued the work. These experiments are exceedingly difficult. Getting the surface of water really clean on the day that your lasers then operate and function is really very difficult. And so it's taken 2 different theses to produce the kind of data that you've seen today. And Eric Chamet's been the leader of the calculations, and Fred Moore from Whitman College, who comes to visit us summers and is now on sabbatical with us, has been enormously helpful in all of this effort also. So I thank you very much for letting me tell you this quick story about gaseous absorption of water surface, but I hope you appreciate, too, that it's the beginning of what I think will be a long run of understanding gaseous absorption at water surfaces. So let me just say a few words about Coach, and then we'll come back to the question. So I've always, as a teacher scholar, I've always been very interested in issues of education, and particularly where there is no need. I mean, where there is a lot of need, but there's no obvious solution. So many years ago, Marianne and I were talking back in the mid-'90s, and we were talking about the fact that we were seeing that a lot of women in the sciences were having a hard time making it up their career ladders, especially when they reached mid-career. And so we were brainstorming on what we might do about that, and that led to the start of Coach, which is an organization out of the University of Oregon. And I don't have the website on here, but it's coach.uoregon.edu. And what we got together a group of women chemists, many of which were teacher scholars, and started talking about what we could do in order to change things. And so we developed a series of workshops that we run before American Chemical Society meetings. It's funded by NSF, NIH, and DOE. And these workshops teach negotiation, leadership skills, just about everything, communication skills, how to give effective scientific presentations, all the things that the women felt that they needed when actually the guys need it too. So we have now had over 7,000 scientists attend these workshops that are also held at universities across the country. Universities hire us to come in and do these workshops for their faculty and their graduate students and their postdocs. I just left Atlanta, where I was day before yesterday. I gave a negotiation workshop, 3-hour workshop, to 200 bioengineering male and female graduate students and postdocs. So once in a while I get drawn in to do this, and I very much enjoy it. But what it's taught me is that there's a lot of professional development that we don't teach our graduate students and postdocs, and we need to do a better job of that. We need to create programs in our academic departments that are similar to what you would get in a business school on negotiation and leadership training. Where Coach has gone, and so we've been at over 160 different professional meetings and at 67 or 68 different universities across the country. More recently, in the last 2 years, we've moved internationally, so now we're working with women scientists in developing countries, and we're working with pulling together women scientists from the U.S. to couple them with women scientists over on scientific issues that are of global need. So that would be water, energy, environment, HIV/AIDS, diseases, to see if we can develop partnerships that then can help the women in those countries advance their careers, but help the women in our countries to also appreciate the dire consequences in these countries so that their research might be used in ways that they never saw before. In some countries, we involve both men and women because, particularly in Africa, many of the scientists we work with believe that the males are just as much a disadvantage as women, so we welcome men to be involved also. We currently have projects. 2 weeks ago, I finished a series of workshops in Cameroon and Gabon, which is in central Western Africa. And then in the summer we were in, and then a few weeks before that we were in South Africa. We did workshops in Mozambique. In July we're working in Kenya, we're working in Korea, we're working in, this next month we'll be in Santiago, Chile, a geosciences project on natural disasters. And then a year from now we'll be in Brazil on hydrology, natural disasters, associated with water. So if you have any interest in being involved in what Coach is doing on these projects, you can go to the Coach website and sign up, men and women, and you can, membership is free, and it costs, we have about 500 members to date. So anyway, that's my little break for advertisements for what Coach is doing. It's been enormously rewarding and with many challenges still ahead. Okay, now let's go back to the science, see if I have any questions on the science. Yeah, so what she asked is if we had done it on a more of a solid ice surface, and no, we haven't. And it's kind of tough for us, too, because we can't, it's really hard to these experiments once you freeze the surface down, because we tend to get icebergs, and they kind of scatter. So, so we'd have to do the calculations, but Valerie, no, we haven't done that yet. Mm-hmm.
So I missed why, whenever the sulfur comes down, it's pointing down, right? So I missed why it's oriented towards the interface, but once it goes into the bulk phase, that it still points down and not towards the interface.
Yeah, so it still points down, and it's just the first couple of layers, so I think it has more to do with once it gets there, it's the potential. But the reason it points down is because of the difference in electronegativity between the sulfur and the oxygen. And so that's what actually gives enough of a pull to it to be able to come down. But once it goes into solution, once it goes into 2 or 3 water layers down, then it becomes more random in its orientation. It's just that first kind of a layer, which has a bit of a potential that's there.
So, Jerry, do you see the state of the sulfur dioxide on the water as a well-defined enough state that you could correlate, say, with concentration of SO2 in the in the air above it? You could look at thermodynamics of the state, the population of a state. That is, that you would see binding statistics or binding concentrations with concentration of SO2. Is it could you define a binding energy? Could you define thermodynamics in the way you would in surface science?
Yeah, Alex, I think you could. I think you could. You have to we haven't been able to do it because we haven't put enough controls on our flow over the water in this first stage. But I think if you did them very carefully and you did them as a function of temperature and then you did them as a function of concentration, I actually think you could. I really do think that we eventually will be able to get to the point at a water surface that people have done like you have done so beautifully on solid surfaces. We're just not there yet.
And you need your laser to work every day, I'm sure. Yeah.
That's right. That's right.
So, Jerry, can you look at the effect of impurities in the water on either the structure of the SO2 that forms or the relative flux into the water layer?
Yes, so that's a great question. So we've actually done studies. It would just be too long for me to talk about them here. This thing's in the way. And that is that what we've done is actually put organic films on the surface. So we've put formaldehyde on the water surface and looked to see what would happen. And it turns out that you have to get a complete slathering of the surface, and that's hard with the organic on the water surface. And so when you get that organic completely covered on the water surface, then the free OH completely goes away. And so then you can't monitor this coming down. But in the intermediate case where you can do, where we do some formaldehydes, just a very low coverage, you see that it changes it a little bit, but not that free OH bonding, but not very much. Now, regards to impurities, impurities are just deadly because they kill off the free OH. And of course, you know, in the laboratory you have all kinds of, even if you were in a really clean laboratory, you have all kinds of stuff in the air that chooses to land on the water surface. And so you have to be really careful with the experiments because you have organics showing up on the surface all the time if you're not really careful. And in that case, and so we've tried to avoid having organics on the surface and be as careful as we can unless other than these formaldehyde. Now, you can also just throw stuff in the water surface. We've done a lot with regards to salt, so you completely salt up the surface like you would have in an atmospheric aerosol kind of a conditions. And then what you find is that those ions, even when you load it up with a lot of ions in solution, they don't make it to the top layer. They're like 1 or 2 layers down. And so they don't affect that very top layer, but they do affect how much goes in, just like with the sulfuric acid. But there's sometimes where some impurities, I would call impurities, but they're actually ions that you put in. And in some cases it enhances the uptake, but you just don't see very much of a change in that free OH unless it's playing with the equilibrium like I talked about with the sulfuric acid.
Yeah, following up on that question, I'm curious for the water droplets that are in the atmosphere, to what extent you can think of those as clean water, or whether you should really think of them as coated with organics or disturbed by other impurities or things out there in the environment.
Yes, so that's a great question. What's in the atmosphere is actually increasing. In the last 5 or 10 years, there's some increasing evidence that they're actually coated with organics. And a lot of these organics are the formaldehyde, which is why we have done the formaldehyde experiment and some of the other organics. They're really a soup. They're a soup of sulfuric acid, they're a soup of nitric acid, they're a soup of all these different ions there. So what we've been doing also is to be studying the surface of these very acidic solutions, and then also not only what SO2 does, but also the acid itself. And interestingly, what we find, and the reason we've been interested in these acidic surfaces is because if you have a very strong acid in bulk, like nitric acid, does it have the same reactivity on the surface as it would in the bulk of nitric acid? And nitric acid is just a great story, because what we found is when you have nitric acid, concentrated nitric acid solution, the nitric acid at the surface doesn't dissociate. So it's a very weak acid at the surface, whereas it's very strong once it's in solution. And that's because the nitric acid sits at the very top layer, and not much water can get around it to yank the hydrogen off. So that was more than you probably asked, but I wanted to share it.
So first, I think it would be good if we introduce ourselves when we ask questions. So I'm John Tully from Yale, and my question has to do with timescales. Do you have an idea of how long it takes for SO2 to get from the surface inside? How many molecules have to move around?
Yeah, so the calculations would suggest that it's pretty quick. It's on the order of several hundred femtoseconds, but we don't know from the experiment. You know, it's if someone is doing time-resolved some frequency experiments and set up to do that, this would be an ideal experiment for them to be testing, because you could look at that free OH as a function of time as you put the SO2 on, and so it's well set up for someone that wants to do those kind of detailed experiments. But all we can do is to get it from the calculations, and the calculations say it actually goes in pretty quickly. So then the question becomes, how much do you have that might just be going straight in, or what's the ratio of what's sitting at the surface as a complex versus what's going into the surface?
I'm Jim Anderson. Is this on? From John Tully's sister institution. This is fascinating. We were involved in looking at the way water is injected into the upper troposphere as a climate link to understand how the outflow from these convective events affect infrared trapping. And in the process of doing this, discovered that water is injected deep into the stratosphere over the United States in the summer from these storms that are getting more and more popular, which was a complete surprise. And the reason that links back into this is that it's the ubiquitous sulfate water aerosols that are executing the conversion of inorganic chlorine to free radical form. And we track this in the Arctic lower stratosphere in the winter, that, as you know, has led to massive ozone loss.
Yeah.
Except now, this is exactly the same chemistry. The temperature is a little higher, but the water vapor concentration from the convective injection is much higher. It's running 10, 15 parts per million. So the kinetics is exactly the same, except it's the inverse problem where those aerosols are taking water on rather than taking sulfate on. But the key thing is that it enhances the loss rate of ozone by a factor of 200 to 300.
Oh, good heavens.
But this is in the lower stratosphere over the United States in the summer, not over the Arctic and Antarctic in the winter. So this has opened up, first of all, a connection between climate forcing by carbon dioxide affecting severe storm intensity and frequency, but it links right back into the sulfate chemistry and directly into ozone loss over populated areas. So we were studying climate at the time, but we're shocked. So we'd like to continue this discussion, but invert the question and ask how water comes onto a sulfate water mix.
You know, that's very interesting because I gave a talk related to this a month ago at the AC or whatever, at the American Chemical Society meeting, and someone said to me, you talk as if the water comes up to get the sulfur, but why don't you talk about the fact that the sulfur comes and grabs the water? And actually it's the sulfur that's the temptress so much as the water. So it ties in exactly with what you were just saying, so we should talk more. Great, thank you all very much.